Let's continue. In the last class, we began to spell out our rules for calculating scattering amplitudes for the string. And the rule that we finally arrived at was as follows. First, we defined this picture changing operator by taking the BRST current and integrating it around the zeta insertion, where zeta was the BC system in the bosonization of the beta numbers. Okay? And then our rule went as follows. We should put all our vertex operators in the picture that conformity theory suggests, namely the vertex operators dual to the appropriate states in conformity theory. So in the NS sector with an e to the power minus 5, e to the power minus 5 tilde, that is the corresponding primary matter operator. And if we are calculating a scattering amplitude involving n point functions in the NS and S sector, we will in addition put n minus 2 copies of the picture changing operator somewhere on the world sheet. Where on the world sheet we put these picture changing operators didn't matter, because we showed that the amplitude was independent of the location of picture changing operators. Okay? And then we also argued that there was a particularly simple way to think of this amplitude. That is by taking picture changing operators and bringing them near to, making them coincide with n minus 2 of the vertex operators. And that particular prescription changed the vertex operator from being in the minus 1 picture, being in the 0 picture, meaning that the vertex operator had no power of equal past I once we did that. And also its net effect was something that we earlier guessed in more intuitive grounds. That is to act with the vertex as a primary vertex of primary matter operator corresponding to that vertex insertion with a g minus half, g tilde minus half. Or equivalently, if we thought of the primary operator as the lowest component of a superfield, to integrate that superfield over the zeta and zeta. Okay? So, if we were interested in calculating endpoint functions in the of both the all of the NS system, the rule could one way of forming one implementation of the rule would be to put two operators in the natural conformity theory picture. The other n minus 2 operators in this other picture. That is, drop the e to the power minus 5, take that superconformant primary as lowest component of superfield and integrate it twice with the string. Now, this is not unique. We could take all n minus 2 picture changing operators and bring them near one of the operators. So then, n minus 1 operators will be in the natural conformity theory picture, and this one vertex operator will be in some very funny, vertex operator. Okay? So you see that corresponding to any vertex operator, there are an infinite number of different vertex operators, all of which, with appropriate other insertions, will give you the same scattering amplitudes. The infinite number of different vertex operators are obtained by taking the natural conformity theory operator, bringing one picture changing operator near to it, 2 or 3 or 4, up to infinity. The powers of phi associated with doing this is, and each time you bring a picture changing operator near, you pick up an effective to the power plus 1. Okay? So, the power of phi associated with the operator is often used as a label when talking about the operator. So, the natural conformity theory operator, the NS and S sector, is said to be minus 1 picture. The ones we've been talking about are the 0 picture, but you can also work with the 1 picture, 2 picture, 3 picture, blah 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 blah. It's up to you. We've got this formal proof anyway, that it doesn't matter. Okay? Now, of course, we can word all this. I mean, we've been talking about NS operators, but the same thing is true for remote operators. Except for this was zero picture. You see, for these remote operators, the natural conformal field theory vertex operator has an e to the power minus pi by 2. Bringing a picture changing operator near it, so that's a minus half. Okay, bringing a picture changing operator near it will take it into the half picture, and so on. Now there's something here that I want to mention immediately that that we will explore a little more in more detail a little later. Let me mention it immediately, and that is this. You see, something that has seemed, well, so far in our course we have discussed largely how to deal with string theory in detachments. Now there's another kind of question that you might wonder about. And that question is how to deal with string theory in an arbitrary curve pattern. Now, of course, in string theory, it's the theory of gravity, you can't work in any pattern. But you should be able to work in a background that solves the equations of motion. Some appropriate solution of Einstein's stringy corrected Einstein equations. You should be able to look at string scattering. That's what happens. And as I've alluded to many times, so we haven't gone through this properly yet, we will. As I've alluded to many times, the answer is just some sort of sigma model. Okay? The answer is just some sort of sigma model. For instance, in the context of the Bosonic string, instead of dealing with eta mu nu, del x mu, not by 4 prime, you deal with g mu nu of x del x mu. Okay? And if you have a B field turned on, you add in addition the object B mu nu del x mu with it, where when the derivatives are contracted with an epsilon test. Okay. Now, part of the logic for this enhancement goes as follows. Suppose we take the metric field, and we consider to start with metrics that are flat space plus a small fluctuation. Then G is replaced by eta plus H. Okay? So then the thing that you have added, H mu nu del x mu, is precisely the vertex operator for a graviton whose wave function is given by H mu nu of x. Of course, if it's going to be obey its linearized equations of motion, this H mu nu of x is equal to, it takes its form into pi k dot x, or some linear combinations thereof, where k squared is equal to 0. Now, those are the solutions to the linearized equations. So you get precisely the vertex operators that you were allowed to scatter. Okay? So you see that enhancing to this study of string theory in an arbitrary background manifold, the study of strings propagating on an arbitrary sigma model, infinitesimally can be understood by exponentiating a vertex operator. Okay? Which is usually the kind of thing that we do when we want to give a condensate to a given field. Okay, there's an interesting story here about how the conformal invariance of this model determines the equations of motion, and I'm sorry we haven't gone through that. It's a very basic, very beautiful aspect of string theory, but somehow we've not got into that yet. We will. Okay, but let's forget about that. The point I wanted to make at this point was that look, when we started with a nice sigma model, the sigma model had no ghosts associated with it. Then we added to it the vertex operator corresponding to a given field, and we got another nice sigma model. All this went to the Bosonic string. Now it would be pretty miserable if this nice feature of exponentiating vertex operators to get a sigma model was the feature only in the bosonic string that didn't carry over into the superstring. It would be an unfortunate, sort of almost unbelievable state of affairs. However, immediately when you start thinking about it, it seems very different in this superstring. Right? The vertex operator for the graviton was, if you remember, it was psi mu hmu of x. But one shall be pi x. Not only that, this has an e to the power minus pi and e to the power minus pi. So if we add a little bit of this vertex operator to this action, what we get is terms that involve psi mu, terms that involve superconformal ghosts. It looks nothing like changing this eta to eta plus h. Okay? Moreover, this looks like a very strange thing to do from many points of view. One of which goes as follows. As we know that in order, suppose we add this, we just experimentally added this to this action to check whether it corresponds to working in a deformed background field. It's sort of clear that it doesn't, for the following reason. That, as we've seen before, any given vertex, any given scattering amplitude, because of the phi shift symmetry, phi shift conservation number, any given scattering amplitude has to have a given violation of net phi charge. For instance, on the sphere, the violation of net phi charge has to be by 2 units. Okay? So if we added this to the action and then formally took that action and started power series expanding the coefficient of this term, in any given scattering amplitude, only one of the terms that you bring down could possibly contribute. Because the terms that you bring down each have different charges under phi translation. And not all of them could saturate the same. Could saturate the same the phi conservation law simultaneously. Okay? So this doesn't at all look like the right kind of thing to do to get some sort of finite deformation of the original action from several points.
But is it true that if you go to a zero picture?
Yes. Now, it's this picture changing business that gives you a rather natural resolution. If you take this vertex operator and go to the zero picture, all these problems are solved in the NSNS. The main problem with the NSR string theory with Ramon, there's a big unsolved problem with NSR string theory with Ramon fields. That is that there is no Ramon field vertex operator in the zero picture. Okay? So everything that I'm saying now will work for the NSNS background, it will not work for that. So we don't understand how to write down NSR string theory for string backgrounds with a non-trivial Ramon field. So we don't know how to write down string theory in ADI 5 for S5, for instance, in the NSR format. There are other ways of writing down string theory, namely most notably the Berkowitz formalism, it's more complicated, but have several nice features that allow you to study string theory in background of fields. Okay? But the key point here is that Ramon sector vertex operators do not have a zero picture. Do you mind with puzzle?
Because in some sense, even here, if you are looking at this kind of vertex operator, it seems that such a thing is not possible.
What is not possible?
I mean, small deformations of this background is not possible if we stay in this picture. But there exists a picture where such a thing would be possible.
Yes.
And but is the statement that for the Raymond sector it is never possible? Or
there is no known way of doing it. To make a statement,
there should be a way.
There should be a way for sure. And the other ways of writing string theory, which are presumably equivalent to this, because they give the same scattering amplitudes weighted to both scattering
So you're saying this picture changing business is not complete?
Right. That if you want to deal, yeah, what is? There is no known way of working with string theory and Ramon backgrounds in the NSR. Now, as I said, there should be some way. It could be very complicated. Yeah, but there should be some way. You know, one way of dealing with this would be to find the explicit map between the Berkowitz formulas and this thing, and to see what his deformation corresponds to in this language. Yes, there should be a way, but it's just not understood what it is. I'm not sure if the answer is in picture changing or something else. Yeah, maybe you will say. Okay. Fine. However, let's stick at the moment to the NSNSA. This is actually a very important point. It points to a fundamental limitation in the NSR formulation string. Okay? That while it allows you to calculate perturbator amplitudes for any string background that does not involve the bottom fields, in sort of principle we don't know how to exponentiate this for Ramon fields. That's something that has been tried a lot, as you can imagine, but has never worked.
Are you using something in this bosonization business? Somehow that is responsible.
You know, nobody forces you to bosonize. If you want to work in the original variables, you can. I sympathize. There should be a way. You know, maybe if the right people think it through, they will find it. But probably that there's some way. But of course, it shouldn't be forbiddingly complicated. It should be possible to deal with in the sense of do calculations. And yeah, okay. Fine. But yeah, so that's very, very important. It points to fundamental limitation. Well, no, maybe not fundamental. A limitation on a current understanding of NSR perturbation. Yeah? And is one of the important reasons why at some point in this course I'm going to describe for you the Berkowitz formulas, which does not solve it. Okay? But at the moment we're still far away from that. So let's take this business and try to understand it in the NSNSA, yeah? Where it does make sense. You know, where the zero picture makes sense. So to start with, so that all of this was just throwaway remarks, but it motivates the following exercise. Let's try to take this operator and compute what it is it is. Okay? So we know what the calculation rule for doing that is. The calculation rule is to construct a superfield. Okay? The calculation rule was to construct the superfield whose zero component this guy is. We're going to be dropped. But first step is drop this. Drop the post parts. Construct the superfield whose zero component is this object, and then do the theta binding. And that's a simple way. Because you can also act with G minus half. This is even easier. So it's even easier because we set up what we needed last time. You remember, we had the superfield del X. Oh, okay, I'll just remind you what we talked about last time. We had the superfield X, which was equal to capital X, which was X plus theta psi. Was there an I? I kappa psi bar plus theta r. Okay? And then we worked out the superfield del X. Okay? So del X was equal to del theta plus theta del Z. Okay? So we got the superfield del X, which was equal to so del theta, which gave us I times psi, and something plus f. But you remember that f was just 0. So auxiliary superfield of the solver is in the end just set to 0. I'm going to ignore the f. Correct? So we had I times psi plus theta times theta times del. Now, this theta times del has two pieces. There's theta bar times del of psi bar. But by equation of motion, del of psi bars. So we can ignore that. Okay? So there's plus theta times del x. So effectively, after using equation, okay, big D of this capital X superfield is psi plus theta times del x. Okay? Something nice about this. This is an entirely holomorphic field. This big D on this capital X is an entirely holomorphic. Okay? Notice now that this is a superfield whose lowest component is psi. Okay, so let's put mu in x here, we get mu. So, if we want an object whose lowest component is sine mu times e to the power I k dot x, if we want an object, a superfield that has this as its lowest component, that's a simple way to get it. It's simply, this is psi tilde, this is del x mu, del bar x mu, capital X times e to the power I k dot capital X. It's clear, you take this superfield and you restrict the theta equal to theta bar is equal to 0 and you get that object. Now we want the d theta bar integral of this object, which means we want to take this object, expand it to order theta bar and look at the coefficient of theta. So let's do that expansion. Okay, so ignoring negation. Okay, let me do the expansion. Let me do it as honestly as I can, and I might have to fudge some i's and so on. Wait. Okay, so this is sine mu minus I theta del x mu. This is psi tilde mu minus I theta bar del bar x mu. And this object is the whole thing. It's e to the power I k into a mu x mu plus theta psi mu plus I times theta bar psi bar. Again, I'm saying x. Okay. Now I'm interested in the theta bar component. So how do I get it? Okay. One way is to keep theta from here, theta bar from here, to keep 1. Okay? Okay, it's clear that e to the power I k mu x mu is the overall outside. Okay? So you get e to the power I k mu x mu. And one thing that we have is theta bar times del x mu del x bar. And del bar. Okay. What else do we have? We have what we get by expanding this to first order theta and theta bar. And what we have by expanding to second order theta and theta bar. So, let's do that expansion. So, let's first look at the things that you get from first order theta. So, you can take the theta term from here and the theta bar term from here. Do something else, right? So, let me tell you the 4 kinds of terms we're going to get, and I'll write down the answer to this. We have to combine here. See, what are the terms? You could get theta from here, theta bar from here, psi, psi bar, psi, psi. Okay? That would be a 4 psi, a psi, psi, psi bar kind of term, with 1 psi and 1 psi bar contracted with the k. Okay? You could get a term which is sine from here and theta bar from here. Sorry, theta from here and theta bar from here, and this guy. Okay? Which would be a term which is psi bar, the whole thing squared, one of the psi bars contracted with the k, and a del x. Or otherwise you could get a term which was del bar x with this guy and this guy. Okay? Which would be psi the whole thing squared, one of the psi's contracted with the k, and a del bar x. Okay. So you see that there's a total of 4 terms. This term will be written out, del x with del bar x, then psi k psi contracted with psi bar k psi bar, psi k psi contracted with del bar x, and psi bar k psi bar contracted with del x. Okay? Now, the terms are exactly what you would get, at least up to sines and i's and so on, by expanding out I times del x mu plus half prime psi. Okay, in the superfield language we were working with alpha prime equals 2. So this is but we restore it kind of.
We get this after integration or
Let me try it. Yes, after. It's the theta bar. Plus I del bar x mu plus k dot psi tilde mu times phi. Is this clear? This term is the term we already written down here. And the remaining 3 terms are the terms of the sort we talked about. The scale of psi with either del bar x or with psi bar, right? And this. You see that all of these kinds of terms are going up here. You have to keep track of the signs and so on carefully. Okay? But this is what you get. Okay. Okay. And if we work with superfield language, we will get it like this. So then dimensionally you restore alpha prime. You get your alpha prime. Or you work with superfield language keeping alpha prime in the expansion also. Okay? It's a sort of nice exercise to get the same operator by acting with g minus half tilde on it by k dot x psi psi. It's simple but nice exercise. Okay? Is this clear? Now you see that in this zero picture, there is a term that reflects the graviton as we knew it from the bosonic string. Just del x, del y. But you see there's more. There's interaction of this stuff with the fermions. Okay? This additional stuff reflects the fact that that if you want to take the flat sigma model and deform it in a way that changes the x's, you're not free to completely do that. You're not free to change the x's and the size completely independently, because the theory has to remain n equals 1 simple. Okay, so change in x must be reflected in the corresponding change in 1 simple size. Okay, and when we study the sigma model in more detail, we'll understand that. Okay, but that forces such a change in x to be accompanied by a corresponding modification of the psi bar. In particular, there's a psi to the 4 term in the action, which this term catches.
So this second term in the first one, what is the I?
Why is there an I? Oh. Okay. Okay. You want the only thing that's important is relative factors. You want to know why there's a relative factor of I between this guy and this guy. Okay. So the two terms we have to compare from this point of view are the term that we get. Right. So the term that we get when we choose.
Okay. So when del bar x dots with psi.
When del bar x dots. You want this? We want to compare this term and this term. Okay. Okay. So the term where del bar x dots with del bar x
Doesn't have an I.
does not have an I in view. The term where
Del bar x dot with psi.
del bar x
Dots with psi.
del bar x dots with psi, you say also doesn't have an I.
No, it should dot with that.
Wait. No, we want theta bar here, theta here, and nothing. Oh yes, it does have an I. That's I with I.
Okay.
So the three I's. Okay. Other questions, comments? Okay, good. Now, let's use this immediately to calculate it. Okay. We basically completed everything that we needed to know about calculating scattering amplitudes in order for you to calculate any tree-level scattering amplitude that is likely to be of interest to you. Certainly in this course, possibly. Okay? However, of course, in order to see these rules at work, you need to do lots of calculations. When we were studying the bosonic string, I did a lot of these calculations to you on the board. I have a proposed modification of this plan. I'd like one of you to volunteer to come in one of the subsequent lectures and compute for us lots of scattering amplitudes. Just so that the person who does it, the person who does it will learn much more from that than by sitting through it. And that's a substantial fraction of it. 1 by 6 of you will learn. Will learn a lot. Okay. That person may also want to volunteer, or maybe another person will also want to volunteer and compute some one-loop scattering amplitudes. So that would be a little bit. Okay. So maybe we could have a volunteer for this coming Friday for about half an hour to compute half an hour, 45 minutes, or however long it takes to compute some tree-level scattering amplitudes. By the end of this class, I will ask you for one. We'll fix a name. Okay? But just to start this process and just to see how this thing is working, I'll initiate one calculation. And the calculation that I initiate is a 3-point function of gauge bosons in type 1. Okay? So there are various details that this person who's doing this calculation will fill in around the chat fashion factors and so on. Because all of that works exactly like in the bosons. Okay. The new element is the vertex operator. Okay. So what have we got? We've got this. We've got 3 insertion points. Well, 3 gauge points. Okay. Now, with these 3 insertion points and 3 gauge bosons, we've got to put in 3 vertex operators. As we know, this is like half of the sphere. Okay, so whatever rules work for the disc, for the sphere work for this as well. Okay, so in particular, our rule says that 2 of our vertex operators should be in the natural gauge theory picture, natural conformity theory picture. Whereas one of it should be in the 2 of the vertex operators should be in the -1 picture. One of the vertex operators should be in the 0 picture. So that's what we should do. Right? Of course, I've discussed here the closed string. Everything carries through basically without modification to the open string, so that you have only one factor of, instead of having holomorphic and anti-holomorphic factor, you just have one factor. That's as usual. Okay, good. So, what is the expectation value we have to calculate? What we need is, so suppose we've got gauge boson 1 and 2 with momentum K1, gauge boson 2 with momentum K2, and gauge boson 3 with momentum K3. Okay. Let's say this is polarization E1 mu, this is E2 mu, and this is E3 mu. Okay. What conformal theory calculation you have to do to calculate this correlation? Well, let's separate it out firstly between matter, conformal hosts, and superconformal hosts. Okay. Firstly, from the point of view as a conformal field theory, as in the bosonic string, all 3 vertex operators are fixed. Because there are 3 conformal field vectors in the disk. Okay? So, the conformal hosts, if this is, let's say this is fixed at point x1, this is fixed at point x2, this is fixed at point x3. The conformal host diagram we need to calculate is C of x1, C of x2 is C of x3. This is exactly as follows. Okay, what about the superconformal host part? Well, according to our rules, 2 of the operators have to be fixed into the -1 picture and 1 in the 1 picture. Let's say we choose 1 and 2 to be the 2 guys that are fixed in the -1 picture. Okay?
You're taking both. You're acting one picture change operator.
1 picture change operator on the third one. Yes.
And there's only one.
There's 1. Okay? So, the only host dependence will be e to the power -5 for the first 2, so then e to the power -5 of x1 and e to the power -5 x2. This is what we need for the superconformal host part. And finally, this is what we need for the matter part. Okay? So what we need for the matter part is what? There's E1 mu times psi mu of x1, E2 mu times sine mu, let's call it another, mu times sine mu of x2, also, okay, yes, okay, thank you. E to the pi k1 dot x, e to the pi k2 dot x. And here, there is this whole object. There is x theta dot plus alpha prime by 2 k dot k3 dot psi into psi theta, the whole thing dotted with E3 also multiplied by e to the power k3. these x's are all at different points. This one's at x1, this one's at x2, and this one's at x3. What? Theta, I just use this as my index for the free. Theta is not the fermionic one. I use the free, dummy index mu here, dummy index mu here, and dummy index theta. This is E3 theta. Suppose this is x dot. I've written x dot because it's on the path. Okay. D by dx. It is like x, but I don't know. Okay?
This is what you get if you integrate what you want.
If you integrate what you want, you do the whole thing boundary, basically. Yes. Okay. Now, just to see, roughly where this is going, I'm going to work out the x mu dependence, x1, x2, x3 dependence. Just to see. Well, roughly how it is. Let's look at this guy. Do you remember what the answer is? Do you remember what the answer is? Can you simply deduce it? What is the weight of the field C? Nobody remembers what the answer is, sure? What is the weight of the field C? -1. So this object here has to have what homogeneity in x's? It's some function of x1, x2, x3 of what homogeneity? From dimensional analysis, -3 or +3? C is equal to -1, which means it's the same scales like x, not like x. Okay? So it's x to the power +3. It's a homogeneous 3 in the x. Now, C's are commuting or anti-commuting? Anti-commuting. What does this mean for this 2-point function as x1 approaches x2? This 3-point function? 0. Good. So this must be, it's very simple objects. It's a polynomial of degree 3. There's no singularity. There's no singularity in the way of 0. So it's a polynomial of degree 3, which has a 0 when x1 approaches x2, x1 approaches x3, x3 approaches x2. Can you tell me what the answer is? It's x1 2, x1 3, x2 3, up to a sign or no right number. No. Actually we worked it out. Yeah, okay. So, up to things that we usually don't care, that people usually don't care about unless they're writing a paper. It's this one. Where x12 is x1 times x2. Yeah. What is this object? What is this super? This is harder because you have to remember a little more. Not sure. But those of you who were there last lecture should remember that this guy was, the singularity in this was 1 over x1 minus x2. Okay? Then translation and there it says you have to be. Okay. So, e to the power minus pi of x1, e to the power minus pi of x2. This is equal to 1 over x2. Now, well, you can inverse both sides. Yes. Yes. But actually, this is just a free field. This is just a free field formula. How will you deduce it? You deduce it using mixing. Because these are free fields, this object is equal to e to the power plus half of expectation value phi of x1 phi. Actually, this not even a half. There are two terms. Meaning, now how do you deduce whether it's a half or not? You just Taylor expand. Yeah, so there's no half, right? Because the Taylor expansion, this is e to the power 1 minus phi. This is e to the power 1 minus phi. Those terms appear together with no half. So it's this. And this was equal to minus of log. Okay. So this was equal to minus log 2, which is this. So of course, all these formulas have free fields. You easily calculate, but it's often easy to get it without even the bother of calculating it. Okay? So that's simple. What about these coordinates? Now that looks like more of a mess. Okay? However, it's not really such a mess. So as far as the size go, they're free fields, you just pick contract. Okay? The only thing that's a little tricky to remember is what you do with these x dots in these combinations. Okay. Okay, fine. Then let me remind you. E to the power I k1 dot x, e to the power k2 dot x, e to the power k3 dot x, so any number of those, we have this nice formula. When e to the power I k mu x mu at sigma I sum over I. It was a simple generalization of this formula, which went is equal to e to the power minus k mu I k mu j times expectation value x mu sigma I x mu sigma j. Where I and j are summed over distinct pairs. And we don't allow I to be equal to j because the operators that are inserted in this thing are all valid. Okay? And this object then was what? It was minus alpha prime by 2. Minus alpha prime by 2 k mu I k mu j log of was there a phi 2 with the open string? Wait, no. In fact, it's a 2 alpha prime. 2 alpha. Okay, log of xi minus xj, which then is equal to, but there's a minus from here, and there's minus in the log formula, so that goes plus here. And then that is equal to xi minus xj to the power 2 alpha prime ki dot kj. Again, product over base. Next, let's agree to purchase. Okay, so if we only had expectation values of this sort, that's also very easy. Okay, but we put one new element here, one additional element here, which is a factor of x dot inside this business. Now you remember that we learned how to deal with that when we were doing these amplitude calculations with the bosonic string. Of course, it's no problem. Of course, you can deal with this. Really? But I remind you of, what was the point? The point was that we did a Gaussian integral with some sources in order to get this result. So that Gaussian integral is saturated by classical solution plus fluctuations. And on the classical solution, x dot has a non-zero value. Okay? The fluctuations are independent of what the classical solution is. So you remember that our net rule was that if we have expectation values of things like x dot here, what we have to do is to replace this x dot with what it is on the classical solution corresponding to all these sources of the exponent, plus an oscillator basis. But the oscillator is contracted by Wick's theorem. Okay? So I'll just remind you of our rule. Our rule, this rule we developed in dealing with the bosonic string 1 year ago. Right? V mu, exactly. Our rule was that this x mu dot is to be replaced by V mu plus Q mu. V mu was a classical dot, Q mu was an oscillator which contracts according to Wick's theorem. We will not have to worry about Q mu because we never have more than one x dot insertion. So there's only one oscillator ever, so it never contributes. We were less lucky when dealing with the bosonic string because there all three insertions were this. So we have to take terms like a pairs of oscillator Q mu contractions as well. This is a simpler formula. Let's forget about this Q mu. V mu on the other hand, took what form? It took the form minus 2i alpha prime sum over k mu I over sigma minus sigma x here, x minus x. Sound right? Yeah. So what we're supposed to do is to sum over all the other insertions. So x here, we've got an x dot here for the third operator. We're supposed to sum over all the other operators that enter here. Okay? That's what the summation is over. All other operators. So in our case, we go over 1 and 2. And you weight by ki of those other operators divided by x minus x, where x is the insertion of the operator you're looking at. So in our case, that would be x3. And this would be either x1 or x2. Okay? So now all the rules are on this. Any questions or comments about this? About this?
So we are now doing this for x.
Well, yes. You see, the XCFT and psi CFT are incorrect. So term by term is products of correlators of the XCFT and the psi CFT. Okay. So
actually there will be two.
there are two terms exactly. Let's now write it out.
So we calculating the first.
Yeah.
I mean, the one we have calculated is actually the thing we size. For that is right. The previous one we calculated without.
Exactly. The previous one we calculated was with four sides. Psi, and this. Right. So since this guy has two terms, there are three terms in the there are two possible terms in combination. There's this with this, and of course these pi differences. Or there's this with this. Okay? So let's first do this with this. Okay. Now, before we proceed, for the particular case that we're looking at, there's an immediate simplification. Okay? And that simplification is as follows. You see, what we have here is a ki dot 2. But each of the vertex operators is on Martian. Okay? So each of the vertex operators of base k square equals. We also have momentum non-Martian. So let's try to calculate what k1 dot k2 is. k1 dot k2 is k1 plus k2 the whole thing squared minus k1 squared minus k2 squared divided by 2. Well, that is equal to k3 squared minus k1 squared minus k2 squared divided by 2. For each of k1 squared, k2 squared, k3 squared is 0. So that's just 0. So this part is just 0 for all terms. Okay? So we get fact that we have to account for it in this term, we can effectively just throw away all these irritating pi k matrices. Because they give you this business, but that's fine. Okay? I'm not with it. So what's left is what we have to do with these guys. Okay, so let's deal with the ghost part first. x12, x23, x31. Then there is there is by x12, that was the part business. And then there's this term. There's this with this and this. That gives you what? It gives you okay. We also need what sin mu with sin mu was. That of course you also remember. Sin mu with sin mu was 1 over x12, just like the c's. Sides are same as c's. First coefficient. Okay, so this gives you eta mu divided by x12. That's the side and side. And then there's v term. So that's times 2 alpha prime times k1 over minus x31 plus k2 over minus x2. No, plus. Okay, these signs, it will be a miracle for you, right? But okay, that's the first term. What's the second term? The second term has contractions of these guys, and you might now think there are many ways to contract these guys. Okay. Oh, sorry. Every time I have a K1 that's dotted with this epsilon. Yeah, sorry. So, yeah, you can ask me.
K1 dot E. It's K1 dot E3.
No, you're right. It's dotted with E3. Yes.
K1 dot E3, K3 dot K2 dot E3. And then the eta is just E1 dot E3.
E1 does. Thank you. Excellent. Okay. Now we have the terms involving the sides. So you might think now there are many possible ways to contract 4 sides with each other. But there aren't. Because you're not allowed to contract these sides between themselves. Because this object is not. Okay. So you have to contract this guy with this guy. And this guy with this guy. Or vice versa. So just 2 ways. Okay. So what do we get from there? We get oh wait, I'm sorry. Sorry, one more mess up. I'm sorry. There's one more mess up that I did. This is 2 alpha prime. For the same reason that the operator product becomes 2 alpha prime for the open string. So the calculation we did was correct for the closed string. We're just guessing the open string answer from there and mistake. There's a little answer. Okay. Good. So now we're in business. So let's contract this guy with this guy. That will give us an E1 dot E3 into E2 dot A3. We'll have a 2 alpha prime, and we will have minus x13, x23, and logarithms is a minus.
No, there's no minus.
There's no minus. Okay, we'll fix that by comparing equations. And of course, then there is the flip. That is the guy where we have this guy hitting this and this guy hitting this. So we will have plus 2 alpha prime E1 dot E2 dot E3 into E1 dot E3 over X 2 3 X 1 3.
What are the killer factors? I there?
Which I?
In B.
In what?
B.
There was another IDC
B mu.
This is IDX. The IDX.
This I want. Okay.
No. So that time multiplied this minus I and gave us.
Yes. Okay. This is this.
And here, the second one, because there's a flip of the first one.
The second one should have a minus sign. That's probably right. Let me just see.
Because we're they're bringing one from the calculator. One way.
Right. So if I contracted this guy with this guy, I bring this through two fellows, so no minus sign. If I contracted this guy with this guy, there would be one fellow, so there would be a minus sign. Yeah, that's right. That's right. Okay. So now that we have this all on the board, now I'm clearing this. Okay, so there's a 2 alpha prime overall, which I'm just going to clear off. You know, 2 alpha organization. 2 alpha prime. Okay. And now so our first thing I just embed is yeah, that looks pretty good. What about the relative signs? X1, yeah, X1, 2, 1, 2. That's perfect. That's perfect. We even have the relative signs correct if we change. Yeah. If we write this as 1, 3, 1, 2, and 3, 1. I just okay, excellent. Fine. So. Now, what remains to process this thing a little bit. You know, if this is all making sense, then it shouldn't depend on the insertion points for the matrix operators, which clearly cancels.
X1, 2 is an denominator. There is an overall factor of x23 and x31, which cancels with these two factors.
X23 and X31, but that was not there here. I thought we would have to use a formality of momentum with the polarization physics.
The second term had the denominator. The first term.
Let's just work it out. Okay, so let's just get a common denominator for everything.
Okay, basically that plus that. in the brackets.
Well, there are 4 terms. Let's just write out all 4 terms. Minus E1 dot E2 over x12 K1 dot E3 over x13 minus K2 dot E3 into x12 over x squared. Is that really 1, 2? That was 1, 2, 3. That was x2, 3. You see, it came from x dot, which had a 3, so it has to have a 3. X2, 3. Right. X12, and then plus E1 dot E2 dot E3 into E2 dot E3 into X13, X23 minus E2 dot E3 into E1 dot A3 into X23 X12. Okay. What was the way to see common factor? Just a minute. Let's read the whole thing. Yeah, the first thing to remember is that E2 dot K3 is the same thing as minus of is the same thing as minus of to the K1.
So this whole thing is basically multiplied by the factor, right? X1
It's multiplied by x1.
Yeah.
Yes. Now, basically what we want to see is that there's no relative x's between these and that everything cancels. One. Okay, let's deal with let's deal with the first 2 terms first. You see, K1 dot E3 is the same as minus K2 dot E3. Because K1 is equal to minus K2 plus K3 and K3 dot E3 is 0. Okay? So these 2 terms remains in 1.
If I combine these 2 terms,
yeah. So
I'm getting 1 by x.
So we can write this as K. Each of these can be written as with the same sign K1 minus K2 dot E3. Right? So we get K1 minus K2 dot E3 into, and then these 2 signs combined with what sign? With a relative minus sign, this is an overall minus, then a relative minus which is plus 1 over x12, that's 1 over x13 minus 1 over x23. So this is equal to minus k1 times k2 dot e3 over x12, x13, x23, but then also x23 minus x13, which is
Oh, I see.
x21. Okay? This is exactly the exponent stated cancel what we have. Okay, so those two terms work fine by themselves. And these two terms also work fine by themselves. Because they have exactly this exactly cancels. x13 and x23. Yeah. So x13 and x23. Okay. Now I'm getting beyond the stage of keeping track of signs. Okay, so up to, so once we've cancelled all the ones, it's k1 minus k2 dot e3. Okay, now here we have k3 dot e2, but I could also write that as k1 minus k3 dot, k3 minus k1 dot e3. For the same reason as we put there, because k3 dot e2 is the same as minus of k1 dot e2, because momentum conservation and transfer sampling. Right? So these three terms are the sum of three terms of the form this plus cyclic. Yeah, all these. This of course was also multiplied by u1 dot e2. So all three terms have the same form. This is a cyclic. Okay. Now, yeah, okay. This is the extent to which I'm going to work out this guy. Now you need to put this together with the Chandrian factors and transform this into a genuine angles diagram. The person who volunteers to do these calculations on Friday will help us with that. I just wanted to help you to show you how all the X factors cancel in this thing. Now after this processing. Okay, great. So this is how it works for the for 3-point functions in the open string. This is actually the simplest calculation, and we took a long time to do it because we were slow and we were remembering many things. This calculation we could do in 5-10 minutes. It's really simple calculation. Okay. And there are other simple 3-point function calculations. For instance, Koczynski has calculations of some 3-point functions of some fermions, some calculations of 3-point functions of gauge bosons with heterotic string. And then some 4-point function calculations, which give you sort of like the Vira sort of all of these are interesting and useful things to do, and I'd like the person who reviews for us Friday basically to lead us through Koczynski up to page 118. From page 111 up to page 118, up to the beginning of section 12.5. Okay? It's all very analogous to what we did for the bosonic string, just using the correct vertex operators. Okay, good. By the end of the lecture, we'll get more. Okay, but let's move. Okay, so that's how we that's how we calculate scattering amplitude for the superstring. It's no big deal. It's basically the same way that we calculate scattering amplitudes in the bosonic string. Identify the right operators, put the positions, blah 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 blah. There's 4-point functions again. We'll have to do one integral that will give us the Vira sort of type. Okay. So I will not say more about explicit calculations of free-level amplitudes in the superstring. Any questions or comments? Any questions or comments before we move to more formal? Okay. Now, Yeah. So, for instance, in type 2 theories, in type 1 theories, all amplitudes involving matter sector. I mean, if you have the gauge boson amplitudes, that determines gauge boson interactions with the gauge units. Then you calculate gravity amplitudes and that is different. In type 2 theories, essentially one calculation is sufficient.
No, but if that one question.
Okay, good. So Logan's question is analogous to the question of how do you see supersymmetry sort of manifestly in string calculations. And that's another big drawback of the NSR formulation. The big drawback is that while the NSR formulation gives you supersymmetric string theory, it's not terribly manifest in its formulation. You see, in a formulation in which supersymmetry was manifest, you would have had one field for worldsheet boson, space-time bosons, the X's, and a field for space-time coordinates, space-time superspace coordinates. Okay? And that's the way the Green-Schwarz and then the Berkowitz formalism. Here, we've got the field for space-time fermionic coordinates would have been a space-time spinner. Here, and because, because we have to have a symmetry rotating the space-time spinner into space-time bosons, it would have been the same kind of field on the world sheet. Here we do the opposite thing. The size which somehow or the other give rise to the space-time fermions are space-time vectors, just like X's, but they have opposite statistics on the world sheet. So, from this point of view, from the point of view of the NSR formulation, space-time supersymmetry is a bit of a miracle. Because we saw that it was arising. You remember, we saw that there was the vertex operator in the cohomology that generated supersymmetry. This vertex operator we made out of spin fields. We talked about it in the argument of trying to produce the right hydraulic theory. So it's there in the theory, and it's guaranteed to work out supersymmetric if the theory is consistent. But it's not very easy to see to see the circle. In particular, so we discussed these torus one-loop diagrams. To get supersymmetry, you have to sum over all spin structures. Supersymmetry is not a feature that is manifest in the diagram with a particular spin structure. So that will be inherited, throughout the calculations we do. So if we're calculating one-loop catching amplitude, in order to see supersymmetry, you'll only see this once you sum over all spin structures. No particular conformity in any calculation you do will see that supersymmetry. Okay? So it's only right at the end of the process that you see the whole thing being supersymmetric, and that's a significant irritation. It's sort of like doing field theory in a formulation where supersymmetry is not manifest, component language rather than superspace language. It's much nicer to do field theory in superspace language, at least for certain questions. So this is a significant second drawback of this NSR formulation. Okay? And there is so much about drawbacks of this formulation that you might be wondering why I spent 3 months lecturing about it. The good things about it is that it has a large amount of simplicity. Well, you may not think simplicity, you may think is the eye of the beholder, but if you don't think this is simple, wait till we talk about it. I mean, it's based on free fields. Everything can be explicitly computed in terms of free fields. Things get hairier. Yes. Okay. Fine. Yes. Okay. So we need to. We missed the chocolates. Break for chocolates. Okay, that was. Anyway, we're too. Yes. Okay. So we just have 3-4 minutes left. I had planned to do this as a 15-minute part of this lecture, then move on to the main topic. Okay. So, the last thing in chapter 12 that I intend to tell you about, okay, and that I intend to tell you about rather than hearing about it, okay, is is to give you a geometric formulation of the prescription to compute and string amplitudes. The reason for doing this is that in the end, this picture-changing business is quite ad hoc. Where did the rule come from? It's quite ad hoc and sounds quite out there. Okay? So if it comes from a more natural-sounding prescription that somehow sounds better, you may be more inclined to believe it than just give it by itself. And also, it's apparently true that there are some subtle ambiguities, and if you take picture-changing prescription, you have stated for your trailer. There's a natural extension of it to higher keys. You just insert the number of picture-changing operators needed to soak up the 5-0 mode on that case. Apparently, that prescription has, at 2 loops and higher, has some ambiguity. It hasn't quite understood quite clearly. But that apparently is resolved when you think of how you got that prescription in a more geometrically natural way. Okay? For both these reasons, I'm going to tell you about a sort of geometrical way of formulating the general rules for doing string perturbation theory in superstring. This basically it will rarely be needed, may never be needed for you for practical applications. But it's sort of nice to go through once just to feel aesthetically satisfied that there's a reasonable sounding rule for superstring perturbation theory. Okay, so in order to start talking about this geometrical way of dealing with superstring theory, I should first introduce you to the geometrical way of dealing with string perturbation theory for the bosonic string. Okay, this goes under the sort of rubric of, well, it's something that we avoided, though I think Jyotirmoy once explicitly requested me to lecture. It's something we avoided for over a year, but now we can't avoid it anymore. Okay, and it's how to deal with the integral over the moduli in the bosonic string in a geometrically more aesthetic fashion than the way that we did things. So, let me first remind you about the rule for integrating over moduli. The rule for integrating, we have some bunch of moduli. So, d, t, n, let's call it moduli t1 to tn. So, let's call it d, t, I, I, d, t. Okay? And then for each modulus, we inserted the following insertion. We inserted a factor of product over I, square root g, is worldsheet metric, g alpha beta, g beta phi, del k, okay, del k g theta phi, and then b alpha beta. You remember? There was such a factor for every modulus in the bosonic string. And this whole thing makes sense in the following way. In thinking about the problem in the following way, the way we did think about the problem when we first introduced the Fourier path integral. You remember what we said was that we have to integrate over all metrics of the same topology, modulo Weyl transformations. Now, we could always use Weyl transformations to bring our metric to a standard form up to a finite parameter. And the number of those parameters was the moduli. So we had to do our conformal field theory calculation on this standard set of metrics labeled by k, and then integrate over tk. But we not measure. This factor gave us what measure. We have to do that integral. Okay? So we're thinking of doing calculations of the conformal field theory with the metric g of tk, integrate and then do the calculation, then integrate. Okay, but there was another way of thinking of it. Okay, the other way of thinking of it, which we also went through when we talked about this, was that, look, manifolds with different g's are different complex manifolds. That is, suppose we try to take, in any local patch, we can always use a while transformation to make the metric dzi dz bar. The only obstructions are available. So what we could do is to take any given manifold to given genus can always be covered by the same patches. Okay? You can take some set of patches, I don't know, and patch them up. Listen. And you can view the manifold, the data of the manifold in the following sense. Say, in every patch I'll always choose my metric to be dzi, dzj. But the data of which manifold you're dealing with is in the transition functions between patches. Okay? Now, there is no more information in one way of looking at the subject or the other. Okay? If I give you a manifold in terms of patches and transition functions, or if I stick to one set of patches with one set of transition functions and give you a set of metrics of this thing, these things are completely equivalent ways of looking at the same problem. But what we're going to try to do is to try to translate our integral over moduli space into an integral over into this language. That is, thinking of the manifold as labeled by its transition functions. Okay? And we've got this integral over moduli, but we want to put this insertion factor that gives us the weighting over the moduli explicitly in terms of the transition functions. We never want to think of a metric. The metric is always flat. What varies is the transition functions. Okay? So this is viewpoint number 2. Viewpoint we never adopted so far. Okay? But then it will be a viewpoint that naturally generalizes to the study of the abstract study of superstring amplitudes, and therefore that we want to adapt in what follows. Okay, is this clear? Okay, so this is the exercise that we're going to undertake. What we're going to do is to explain what this insertion factor. We've got some moduli space, which is a moduli space of either complex surfaces or of these metrics, widely equivalent metrics of given topology. That's the same thing. Okay? What we're going to do is to try to explain how this weighting factor, how it looks in terms of these transition functions. Okay. We're going to soon terminate this because. But anyway, any questions or comments?
So this manifold that you're talking about, are you talking about the moduli space or
any particular manifold is a quantum moduli space.
Okay, so this manifold is the worksheet on which we are doing the.
Yeah. We've actually been through one example of this. You see, suppose we take a torus. We can always regard the torus as being defined on a square 0 to pi, 0 to pi. Okay? But with a metric that changes as we change the modulus. Or we can regard the torus as being the metric flat, but with identifications that depend on tau. And you remember we went through a lecture where we explained the equivalence between these two ways of thinking and how we can use these two ways of thinking to obtain what the weighting in the integral over tau modulus was. If you remember how we did it, first we took this way of thinking and translated it to this metric. Saw how the metric changed as we varied tau, used this formula, and therefore deduced the weight for integration over tau. Okay? I want to do that more abstract. Is this clear? Okay, I don't think we can do it. Let me just start saying. Okay. Okay, so first I'm going to introduce a quantity introduced by one Mr. Beltrami, okay, and it's called Beltrami differential. Defined with an appropriate half. Okay, suppose we've got this kind of picture, and let's say this is the mth patch. Now, on the mth patch, let's say that our metric to start with is dz bar, and we're going to make an infinitesimal change in this metric. Okay? We start with the metric dz bar, we make an infinitesimal change in it, so it becomes something like this. Okay. So, let's say that dk, this is the change under the kth modulus, of g alpha beta in the mth patch multiplied, and then I want to raise one of these at this. I think I want to raise the beta index. G beta is called theta and divide by half. This I will call mu m of zeta.
You are putting that matrix on all these values.
To start with, at modulus t equals 0, the metric is flat. But as I vary, t will not be flat. My initial condition is that. I'm differentiating around the place where it's flat, but it's not flat as function. Okay? So this object here is what Mr. Beltrami in Royal called the Beltrami differential. Okay? And it's a nice object because it's the object that enters this thing. It's this. It's this. Okay? So in terms of this Beltrami differential, this insertion here is simply square root g times g alpha theta b alpha b alpha nu, then mu beta. And I just taken off these. This thing is this, and that is that. And we have to do some of this. Okay? But now we use our assumption that the point about which we're differentiating is flat. So square root g is 1. G alpha beta is flat metric. Okay? So this is the same thing as integral b z